Hello and welcome back to our in-depth journey through the STL. This is day 18 and today we are focusing on a container that often files under the radar but is incredibly useful in the right situations. It is the multi-map. We will look at how it works, when to use it, how it compares to similar containers like map and unordered map, and explore some practical real-world applications. So if you have ever wondered how to handle duplicate keys in STL, this is the session for you. Let's begin by understanding what a multimap actually is. At its core, a multimap is an associative container, which means it stores elements in the form of key-value pairs just like a map. But here's the big difference. Unlike map, which only allows unique keys, a multimap can store multiple elements with the same key. This makes it ideal when a one-to-one or one-to-many relationship exists in your data model. For example, think of a dictionary where one word has multiple definitions or a student receiving multiple grades. It's included in the map header, and just like map, it keeps its elements sorted by key. Internally, it's powered by a red-black tree which ensures the insertions, deletions, and lookups happen in logarithmic time. So it's both elegant and efficient. Let's now look at the syntax. Declaring a multimap is as simple as including the map header and using the multimap keyword. Here we have defined a multimap where each key is a string representing a student's name and each value is an int representing their score. Take note of these insertions. We insert Alice with a score of 90, Bob with 85 and Alice again with 95. This is perfectly valid in multimap. It does not overwrite the earlier Alice entry like a map would. Instead, it keeps both, and the container ensures that keys are kept in sorted order, so Alice entries will appear before Bob in this case. When it comes to inserting elements into a multimap, we have several flexible options. First, we can use the insert function with a pair or take advantage of C++11's initializer list syntax, like we saw earlier. If you have a range of elements, say from another container, you can use range insertion mmp.insert start, end. A key highlight: since multimaps allow duplicate keys, every insertion is preserved. Unlike map, where adding a key that already exists would silently fail or override the value, multimap welcomes duplicates. This makes it reliable for collecting grouped data. Now let's talk about how to access data in a multimap. This is where things differ significantly from a map. A map allows you to use the square operator for quick access like m key, but a multimap does not support this because square brackets assumes a one-to-one mapping of key to value. With multimaps, we might have multiple values per key, so it requires a different approach. Instead, we use member functions like find key to get an iterator to the first matching key, lower bound and upper bound to define ranges, and most importantly, equal range. This gives us a pair of iterators representing the full range of values associated with a given key. In the code shown, we retrieve all scores for Alice using equal range, then loop through that range and print each score. This pattern is incredibly useful when handling grouped data. Just as important as inserting and accessing data is knowing how to erase it. With a multimap, there are three main ways to remove elements. First, we can pass a key to erase to remove all elements that match that key. Second, you can erase an element by passing a specific iterator, perfect when you want to surgically remove just one occurrence. Third, we can erase a range of elements using two iterators. This fine-grained control is powerful, especially in applications where data is dynamic and changes frequently. So when should you actually use a multimap in your applications? Here are a few real-world scenarios. Student grades. A student might have multiple scores over time. You want to group them by name but keep all scores. Word context mapping. Suppose you are building a text analyzer tool and you want to map each word to all the positions it appears in a document. That's a natural fit for a multi-map. Event scheduling. If you are building a calendar or scheduler, you might have multiple events occurring on the same day. You need to associate that single key, the date, with multiple values, the events. These examples show the versatility of multi-map when it comes to modeling real-world one-to-many relationships. Let's now compare multi-map to its close cousins map and unordered map. First, duplicate keys. Only multi-map allows them. Both map and unordered map enforce unique keys. Next, ordering. Map and multi-map maintain sorted order of keys thanks to their underlying dead blocks tree structure. Unordered map, on the other hand, uses a hash table so the elements are sorted. Elements are stored in an unpredictable order. In terms of access, only map and unordered map support a bracket operator. Since multimap can have many values per key, this syntax would not make sense. Finally, time complexity. For most operations like insert and lookup, map and multimap offer log-n performance. Unordered map is generally faster with average case of constant time, but only when you don't care about ordering. This comparison is critical when choosing the right container for your problem. Alright, let's test what you have learned with a hands-on challenge. Your task is to write a program that stores and displays the scores of students. Remember, students can appear multiple times, so duplicate keys are expected. The input might look like this: Alice 90, Bob 85, Alice 95, and Bob 87. The output should group scores by student. So for Alice, you would print 90 and 95. Use equal range to retrieve all the values for each student. This is a perfect real-world use case where multimap shines, grouping data efficiently and keeping it stored. Let's wrap up today's lesson with the key takeaways. Multimap is an STL container that allows multiple values for the same key. Unlike map, it does not support the bracket access operator, so we rely on find, equal range, and related methods. Internally, it maintains sorted order, just like map, making it useful for ordered traversals. Whenever your data follows a many-to-one relationship, like multiple grades per student or multiple events per date, multimap should be your go-to choice. Choosing the right container not only makes your code more efficient, but also more intuitive to read and maintain. And that brings us to the end of today's session on Multimap. I hope you now see the power and flexibility that this container offers, especially when dealing with duplicate keys. If you have any questions or want to explore deeper use cases, feel free to ask. In the next session, we will look at how to customize sorting behavior using custom comparators in sets and maps, a feature that gives us even greater control over your data structure. So I will see you there.